Welcome to Let's Roger That. I'm Gilles. Well, this coming project here is going to be an end mill grinding fixture to sharpen end mills on my surface grinder. Yes, there's all kinds of really great fixtures out there, but hey, why not make one myself? Now, this is what I'm going to make. Something like this for an ER32 collet system. So I've designed my own system right here, and I'm going to walk you through what I've designed. Okay, so let's go through my design ideas. They may change yet. Essentially, we've got two parts to be made, and that is the sleeve that will go inside the base. If you look at this here, that's the base on its own, and this is the sleeve on its own. Of course, it's an M32, so we're gonna have to work through this in millimeters. So essentially, this base here is going to be 4 inches long and 2.5 inches wide. So what I'm going to start with is cutting a piece of 1018 flat bar. Then I'll proceed to drilling and boring the piece, because clearly that has to be done before I make the other part. Now, there's a lot of features in this base, but in essence, this part is pretty simple. What's going to be interesting is milling compound angles. Here's a diagram that better illustrates the various degrees that we have to include in this thing. So at the bottom here, for the secondary end clearance, it requires a 30-degree angle. So that's why there's that angle at the front. Now, the primary, or the center relief angle, as it is called, is the vertical part of it, which is 2 degrees. And then, of course, there's the primary end relief, which is 5 degrees, and that's your cutting angle, right? Time to transpose the measurements and sort of idiot-proof this whole block. Okay, so I've got the block blued and whatnot. I've made a punch mark here to indicate the center of where the hole is going to be. And as noted here on my schematic, the hole is going to be 35 millimeters. This part of the hole, 52 millimeters. Now the other thing I need to do here is I happen to have a punch mark here on the end. And so, why have you got that here? Well, there's going to be a pin that's going to be threaded in here, and the tip of the pin is going to be about 3/30 seconds. So this pin here is going to go into this sleeve here, right? And that's how it's going to get locked in to its various positions as I turn it around to sharpen the end mills. So now I guess you have to decide, okay, how am I going to drill through this thing? Well, I could use some sort of involute cutter on my mill, but then in the end I'm still going to have to bore the rest of this thing up to 35 millimeters, and I do not have a boring head for my mill. So that means I'm gonna have to go to the lathe and put that in the 4-jaw chuck and do the drilling and boring operation there. Okay, before I actually bore the internal diameter of the fixture, it's important to talk about this here. This is the machinery's handbook, and there's lots of information on fits and tolerances, And it's important to understand where you're going before you're doing it. So essentially, this sleeve of mine, let's look at that for a second. It's got to fit in there. It's got to be able to turn, but it's got to remain really steady while the grinding is happening, so that there's no discrepancies between each one of the primary cutting edges. So we need to figure out a fit or a tolerance that is appropriate to do that. So when you look at all this here, okay, so there's a clearance fit. That's what we want. And then we need to figure out which one is appropriate. Free running and close running and loose running, that's all for things that spin. But what I want is a sliding fit. It's not intended to run freely, but it's meant to move and turn freely and locate accurately. Well, that's exactly what we need. So here are the shaft bases, G7 and H6, and the hole bases, H7 and G6. So now we need to go look at what are the tolerances that are associated with these symbols. Okay, so now we're at a table, and by the way, this is in metric. So here we are. So we've got the sliding fit here that we selected. And say, for example, this is a 30 millimeter basic hole. But I'm gonna use these as approximations. So this is the hole size that they recommend, right? So from the maximum size of the hole to the minimum size prescribed, here and here. And then the shaft size would be between here and here to make that fit correctly, which equates to the differences of from this to this. So that's about 1/1000 down to really low tenths. The variance in the tolerance of 0.02 millimeter equals to 7/10. So I'm gonna shoot for a 1/1000 maximum. So it's likely going to involve the boring down to 34 point something millimeter, and then honing the rest. So because my lathe is in Imperial, I'm going to be converting all these numbers as I go along so that I can get things accurate. Let's go do that. Okay, I'm at the lathe, and I've got things set up in my 4-jaw chuck, and as you can see here, this rectangle sits in there, and I've got my sander drill aimed directly at that punch mark. So now it's a question of drilling to 1 inch, and then I'll have to bore up to 35 millimeters. Set up for boring operations, and I made the appropriate calculations. So I'm shooting for 35 mils. That's 1.37795 of an inch. And then currently, after drilling a 1 inch hole, this is the measurement in inches. So I've got 380 thousandths to go. I thought I had around 20 some thousandths left, so I took a measurement. This is where we're at, and we need to be at this, which means I have this left, 25 thousandths and 6/10. Yeah, I'm giving myself 1 thousandths more over this, should I really need to. All right, let's continue. Now my lathe is pretty accurate overall. So I've given myself 25 thousandths to work with until I reach 0. I'm gonna take 23 thousandths out of that and take a quick measurement to see where I'm at. taking the measurement. We're supposed to be at, I'll show you, this is the measurement we need to be at, or up to 1/1000 over. So we're currently at this, so the difference is we're 1/1002 under. 1/1000 of an inch comes out very fast. So what I'm going to do is hone the interior with some emery cloth. When comes time to play inside one of those holes on your lathe while it's running, do not ever put your fingers in there. It'll rip it off. Simple as that. It'll be gone. So what I like to do is I take a stick, just a dowel, just a normal piece of dowel. This is about 5/8. I put some contact cement on my dowel, take a piece of appropriate emery cloth, spin it from the top downward, and then finish it up with a piece of tape, and that's it. I'm in the garage. It's a little bit cold, but sleeves up, glasses on, etc. Right? There you go. It doesn't take long to take 1/1000 of an inch out of here, so I'd rather measure often and be sure. Let's try this. It feels about right, but we'll see. Okay, so I just honed that bore with the emery cloth, and look at this, right? 1 inch, 378,009 and we're supposed to be at 377 9/10. So I'm exactly 1/1000 of an inch over, which is within my tolerance. So I'm done. I'm back at the bench to do some calculation for the next feature that I need to cut. The needle truss bearing, this right here, is 4.1 millimeters in thickness. So I want to cut down 4 millimeters and no more. I want it to stick out a touch so that this part of the sleeve will actually sit on that bearing and above the surface of this fixture. That's it right there. Okay, great. Rinse and repeat. Fit test again. Comes. Now it should stick out just ever so slightly, and sure enough, look at that. This is perfect, and it sticks out just a little bit. So I got to go to the bench with this block, and I don't want to lose my concentricity. So because we're going to flip it over and do this sort of similar thing on the other side. So the best way to do that I've found is put a mark on the chucks that you'll move, and just move to it, right? That way, when you come back and you put back, you'll be indicating against the two that you didn't touch. At the bench again before creating the bottom side of this needle truss bearing seat, and just to make sure I get this correct here, essentially the thickness of the whole piece is 38.25 millimeters, an inch and a half. And we've got 4 millimeters up here. I'd like to have 20 millimeters here, which amounts to about, well, a little more than 3/4 of an inch to indicate the shaft, right? And that should be enough. And then the rest, the 14.25 millimeters, which remains here, will provide 4.1 millimeter for the bearing, 5 millimeters for the nut, that's gonna hold the whole thing, and then space underneath, which is going to be 5.15 millimeters, and that'll allow for when we actually mill the compound angle that will be at the bottom. So that'll give us enough material to avoid encroaching on that nut space. Let's try that bearing. Should fit nice and loose. This time I gave it more space. Yes, that's it. Nice and easy. The next feature that I have to put into this thing is right here. It's the retainer screw. The screw that's going to allow for this to turn and then, you know, to stop exactly at 90 degrees from the other hole. So first thing to do, you need to figure out the hole size we're going to drill. So first thing to do is drill this at 5/32, then drill this up to a certain depth. When I design something, I try to reflect on all the different aspects of the tool that I'm making, and whether there's annoyances there, some, you know, insurmountable difficulties in trying to create something or not. And sometimes it's worth spending the extra time to make something that's a little less annoying to use, even though it's a little more difficult to make. I was originally going to use this bolt as a plunging pin and then, you know, thread it in and out every time. But that's going to be annoying. And I read some bulletins out there from folks that said that annoys the crap out of them. So okay, fine, I'll take that in consideration and use their experience. So I developed a system that would work to do that. So to do a spring-loaded system, you basically have to have something to retain the spring and make the pin want to plunge in one particular direction. So one of the things to think about, say, okay, how thick of a dimension have I got to play with, or can I put in all these features in here? And you can, but it's just going to take a little bit of extra work, right? So if you look at this here, imagine this is the fixture base, okay, and that's an 1/8 wall, an 1/8 of an inch wall, a retaining screw of some sort that has a bore through it to let a pin go through. So let's look at the breakdown. This is the actual fixture. This is basically what it's going to have to look like. Pinhole, which is already made in here, right? A 3/32 hole. So we're going to need an 1/8 of an inch thick bolt with a through hole. The pin is going to go in. Spring's going to go in. The little bolt's going to come in here, the screw, and then the spring is going to get trapped in here, wanting to push the pin inward. And then the knob here, you can pull the knob in order to retract the pin from inside that rotating sleeve. So I hope that makes sense for everyone. These are not actual measurements, but what I did do though is I drew it to scales to get a good feel for whether or not it was feasible to make all of these features. So that's going to be challenging because for all kinds of reasons. For example, like threading into here, you know, a tap has a taper at the front of it, but I can only go 1/8 of an inch deep. So I need to come up with some sort of solutions for all of these. And it's going to be interesting. Of course, materials matter. Here I'm going to use 4140, that's pre-hardened because I want the pin to last. So you got to think about all of these various factors when you build something. I just thought it'd be interesting to go over this just to make you understand how I'm thinking through a project and through the design of these different things. Now it's time for me to really start carving in the different characteristics of this thing, or features. So here are the measurements and what they are, for you that are interested. Now I'm going to bring this down so that I have a pin here that's going to measure 93 thousandths in diameter. So now I've got a machine, the padding part. I'm going to take it down to 1/4 inch, and of course it has to be 1/16 of an inch in depth. So now I need to dive in here at 1/16 of an inch mark and carve that down until I reach the appropriate shaft size, which is going to be 140 thousandths. Okay, it's time to make that 5/16 of an inch little screw. Okay, I'm going to mark the center. Good. Change to my 9/64 bit. That's it for that. Now time to cut it off. There we go. Okay, it's time to drill a 17/64 hole down 450 thousandths in order to accommodate the push pad, which is 1/4 of an inch in diameter. Now I'm going to drill with a drill bit of the letter I, because I'm going to tap the top portion of that thing with 5/16-24 threads. And I'm going to go down just a little bit more than 1/8 of an inch. What I need is about 3 threads, so I've got 4. That's perfect. Back at the bench again, and now I'm going to assemble this little tiny pin, which is going to retain the sleeve inside this bored hole. So I'll put that in there, insert the spring. This is gotta be careful here, you don't want that spring to come flying. Okay, so here's what I've got. This portion is going to get set into a pull knob that pulls out. As you can see in here, got about 1/8 of an inch for that little knob to indicate inside the sleeve. And it's spring loaded, so you can see it moves in and out. And it's quite, there's quite a bit of force to it. Once this thing is set into the sleeve, it's not gonna move. So this is gonna be it for this episode. In part 2, we're gonna continue by milling the additional features in the base of this fixture, and hopefully get to work on that sleeve. So there's a fair bit of work to do. This is going to be a multiple part project. So thanks for watching. Appreciate you coming by. If you like what I do, please like and subscribe. And I always love to hear from you. So please leave me a comment. Take care. Bye-bye.